Hello viewers, welcome to this lecture on coordinate frames and homogeneous transformations. So this is the second lecture on coordinate frames. So in this lecture we will give the relation for a general rotation. So in the last lecture the notation F or M was introduced which represent a rotation matrix . It represents a rotation matrix and it gives the orientation of the Fm frame with respect to the F frame. So it gives the relation between a coordinate, the coordinate of a point R and the coordinate of the same point with respect to M, how they are related. So this F or M represent the matrix relating the M frame with respect to F frame. So this is the meaning, and we have also introduced the fundamental rotation. That is, if we rotate the F frame about its x axis by an angle theta, it is denoted by 100 0 cos theta sin theta and 0 minus sin theta cos theta. So similarly the rotation matrix about the y axis by an angle theta, it can be written as (0 1 0) and it is cos theta minus sin theta cos theta, and the rotation about the z axis by an angle theta is given by 0 0 1 and cos theta okay. So these three are called the fundamental rotation, and in this lecture we will see if the fixed frame, if a frame F is rotated, these are the three axes x, y, z axis, and if it is rotated with respect to a general axis, let us say general vector r by an angle theta, then the new coordinate system will be obtained. We call it as say x1, y1 and z1. So the old frame is F and the new frame is M. So what will be the relation between F and M if the rotation is about any general axis R by an angle theta? So that is what we will see in this lecture. So let us assume that the general vector given is a unit vector. We call it as u1, u2, u3. So the unit vector, so this sum of the square of the coordinate should be equal to 1 and it is rotated by an angle theta. So if we consider this unit vector u1, u2, u3, the projection of this on the xy plane, it is u1, u2, 0. So this point is P, OP is 1. and this point we call it as M, and if it is projected on the x axis and y axis, let us call it as M, N, and this is L. So, O n is u1 and O L is u2 and P m is u3, that is the value here. So, if we assume that this angle x O m, this angle we call it as, let us say, beta, and M O P, we call this angle as alpha, and the rotation matrix is given by this particular formula, a 3 by 3 matrix given by this expression. Now, it can be easily verified that if u1, u2, u3 is 1 0 0, that is the x axis, then we will get the fundamental rotation of x by an angle theta can be obtained as given earlier. So, to prove the rotation matrix as shown in the previous slide, we adopt the following procedure. We will rotate vector OP about the z axis by an angle beta like this. So, it will be fixed in the xz plane. From its original position OP, it has come to the position, let us say, OP1, and observe that this movement is moving from y direction to x direction in this in the negative direction. So, it means that we are performing a rotation matrix about the z axis by an angle beta, but it is in the negative direction, that is y is moving towards x. So, it is rotation of about the z axis by an angle minus beta. Now, OP1 will move towards the x axis. So, it means the movement is z towards x. So, it is a positive direction by an angle alpha. So, by this angle alpha. So, we are going to multiply that rotation about the y axis by positive angle alpha like this. So, earlier we have seen that if we perform the operation rotation or any other type of operation with respect to the fixed frame, then we have to multiply those rotation matrix in the left side. So, after bringing that OP1 to this axis, so let us call it as P2. So, the OP1 has become OP2 vector here. So, it is coinciding with the x axis of the fixed frame. Now, we will perform the required operation because we wanted to rotate OP by an angle theta. So, instead of rotating it at its original position, we brought it to the x axis, and then here we will rotate it by an angle theta in the positive direction theta. So, and now because this OX is the x axis of the fixed frame, we have to multiply that rotation in the left side x by an angle theta. So, now we want to take this OP vector to its original place, then only the meaning will be completed, is not it, the requirement is completed. So, the OP2 will be taken back to the OP1 position by making a rotation about the y axis in the opposite way. So, we have to multiply in the left side by a rotation matrix about the y axis by an angle minus alpha in the left side. So, it has come to OP1 position. Now, it should be taken back to OP position in the reverse way. So, we have to multiply by a rotation matrix about the z axis. So, I will write here rotation about z axis by an angle minus beta. Sorry, earlier minus beta, so here it is plus beta, because we are moving from x to y direction for the rotation. So, this 5 matrix multiplication finally will give the relation between the fixed frame and the M frame. Originally it is fixed frame, after making a rotation we will get a new frame. So, originally we got the F frame, this is our vector R vector. So, after making a positive rotation of this axis, we will get a new coordinate frame, we call it as the M frame. So, the relation between F and M frame, the M frame with respect to F frame is given by the product of this 5 matrices. So, we know the structure of all these fundamental rotation matrix as written in the previous slide. Rotation about x, y, z can be written like this. So, by substituting the appropriate angles in this and multiplying this 5 matrix, we will obtain a expression like this. So, an expression of this form in this way, but we have to convert all this alpha, beta, gamma which was mentioned in the previous slide as follows. So, we can see here this expression OM is nothing but the projection of OP on the xy plane. So, it is nothing but OP cos of alpha, but OP is of length 1, it is a unit vector. So, it is simply cos alpha, OM is cos alpha, and then U1 is ON. The x coordinate of this point P is U1, it is nothing but OM cos beta. But OM is cos alpha, therefore, we get cos alpha into cos beta. So, U1 value is given by cos alpha into cos beta. Similarly, U2 is the y coordinate, that is given by OM, that is OL, and it is OM sin beta. So, it should be cos alpha into sin beta, and z axis, that is U3, it is nothing but PM, this length, and that is given by simply sin of alpha. So, now we can use this relation for U1, U2, U3 cos alpha sin beta etc., along with the relation U1 square plus U2 square U3 square equal to 1. So, in this product we will be getting for example, in this matrix we will get cos beta sin beta terms in the 3 by 3 matrix, and in this expression we will get cos alpha, sin alpha etc. So, when the product of all the 5 matrices comes, we will be able to get these products cos alpha, cos beta, sin alpha, sin beta etc. So, all of them can be written in terms of U1, U2, U3 along with this relation. So, with this substitution we will be able to get this expression which can be easily verified. So, the rotation matrix is given by U1 square into 1 minus cos theta plus cos theta, U1 U2 1 minus cos theta minus U3 sin theta etc. So, we will note that the sign of this one here you can see that it is symmetric with respect to these terms U1 U2 1 minus cos theta, here also it is like this, and u1 u3 is coming here. But the second term is like skew symmetric, that is here u3 sin theta, here plus u3 sin theta, minus and plus. So the terms, there is some kind of symmetry and anti-symmetry combination in these terms which can be observed. So this will be very useful in the later stage when we study the differential transformation etc. using this matrix. So a general rotation matrix is given. Now if we substitute a x-axis in the place of the unit vector, we will get the fundamental rotation about x-axis. Similarly 0 1 0 will give fundamental rotation about y-axis, similarly for the z-axis. So now we will see this structure is useful in identifying the amount of rotation and about which axis a rotation is performed. So for example, a arbitrary rotation matrix is given. So earlier we have seen that a rotation matrix is a orthogonal matrix. In addition to that, it should form a right hand system. So if you give a rotation matrix, then how to identify the axis of rotation as well as the amount of rotation. So for that it will be very useful. Trace of the matrix can be seen from adding the diagonal entries. u1 square plus u2 square u3 square is 1, and here you can get cos theta common, minus cos theta is a common factor, and plus 3 cos theta. So by adding all these 3 we will get 1 minus 2 cos theta. Say R11, R12, R13, this is R21, R22, R23 etc. R32, R33. So R12 plus R21, it will give the sum of this first terms only. So it is 2 u1 u2 into 1 minus cos theta. The other two terms will get cancelled. So we will get from here these values. For example, R21 minus R12 by 2 cos theta, this will give u3 value. Similarly, R13 minus R31 by 2 sin theta will be this etc. So the three form u1, u2, u3, the vector can be obtained as well as how much of angle is rotated, that is obtained from the trace. So for example, if I give a rotation matrix 1 by root 2, 1 by root 2 0 and minus 1 by root 2, 1 by root 2 0, 0 0 1. So it is a very standard form of a rotation matrix. So if this is the given matrix, how much angle was rotated and which is the axis of rotation, we can calculate. u1, for example, u1 is R32, R32 is 0 here and R23 is also 0. So u1 is 0 and u2 is R13, R13 is 0 and R31 is 0. So u2 is also 0 and u3 value is R21, R21 minus R22, that is this 2 expression divided by 2 sin theta. So what is the theta value? It is sum of the trace. So 1 by root 2, 1 by root 2 plus 1. So it is 1 plus root 2. So trace of this minus 1 divided by 2. So it is nothing but 1 by root 2, this expression. So cos inverse 1 by root 2 is 45 degrees. So we will get theta is pi by 4 angle from this formula, and if I substitute it here in this case, we will get the u3 value to be 1. So, it is nothing but it is a rotation about the z axis, that is obviously coming, we already know that it is rotation about the z axis by 45 degrees, that is obtained from this formula. So, generally if we get any rotation matrix using this formula, we can obtain the axis of rotation as well as the angle of rotation. So, now we consider the homogeneous transformation. So far it was considered only about the rotation about x, y, z axis or rotation about any general axis. But if the coordinate frame is translated, that is a fixed frame f is given, and if the origin is shifted to some other position without disturbing the directions of the three axes, x, y, z axis are kept parallel all the time and only origin is shifted to a different position. In that case the motion is called a translation. So, the translation, the new translated origin will have a coordinate ABC, let us say, with respect to the old frame. So, in that case we can write the point, any point P with respect to the new coordinate frame. If you mention it as x1, y1, z1 and the same point with respect to old coordinate is x, y, z, then we will get the relation x is equal to x1 plus a and y is equal to y1 plus b, z equal to z1 plus c. So, that is very clear because the x, y, z old one and the new ones are parallel to each other, only the origin is shifted to a point ABC. So, we can conclude that the old value of x is the new value of x plus how much it is shifted, the origin is shifted, etc. And now we cannot write it in the form of a matrix, as in the case of rotation matrix we cannot write the relation of the translation in the form of a 3 by 3 matrix. But if we slightly modify the structure of representing a vector with 3 numbers, then we will be able to perform the matrix relation. So, instead of representing the vector x, y, z with 3 numbers, if I write a dummy variable 1, so with 4 numbers if I represent, where the fourth number is a dummy value 1, then we can write the rotation, the relation between x and x1, y1, z1 in the following way. This can be written as 1 0 0 a, 0 1 0 b, 0 0 1 c. So, we can write the relation between x, y, z, x1, y1, z1 in this manner using a matrix, whereas for a rotation a 3 by 3 matrix itself is sufficient to indicate. So, to combine both rotation and translation in one particular structure, we devise a 4 by 4 matrix structure which is called the homogeneous transformation. So, a homogeneous transformation matrix represent both rotation and translation in the following way. So, as previously seen, the rotation matrix is R, and because we are having a dummy variable 1 as the fourth value in the vector, so we have to introduce the fourth row also as 0 0 0 1 for the rotation matrix, and the fourth column is 0 0 0 1. So, that should be introduced. The fourth row and fourth column are introduced for a rotation matrix. and for the translation matrix the first 3 by 3 matrix is the identity matrix and the fourth column represent the origin, the new origin ABC that will come in the fourth column. So whenever we write a 4 by 4 matrix which represent a translation, it indicates that the fourth column represent the origin of the new coordinate frame which is shifted from the old frame, and the first 3 column of that transformation, homogeneous transformation, represent the rotation of the coordinate frames. So it combines both of them, position as well as orientation of a coordinate frame. So if we have a coordinate frame F and it is shifted to some other position by making a rotation as well as a translation, then its new position and orientation will be obtained, for example, by this expression. Let us say O1 is the new position of the origin and the orientation is given by this expression. Then we can write this FTM. If it is only rotation, we were using R notation for a 3 by 3 matrix, but here because we are introducing a 4 by 4 matrix for the translation as well as rotation, we use the notation T representing a transformation. So FTM, the homogeneous transformation, is a 4 by 4 matrix in which the first 3 by 3 matrix, the 3 by 3 block, it represents the rotation and the fourth column represent the translation. And then the fourth row, it is a dummy row to take care of the dummy variable 1 in the vector notation. Okay. So this example shows that how successive translation and rotation can be handled when we are doing various types of motion from a fixed frame. First we have a fixed frame and then a rotation alpha about the x axis is performed, then a translation along the x axis is performed, then a translation along z axis is performed, then rotation of an angle theta about the z axis is performed. So if all these are performed with respect to the fixed frame, base frame, here OX represent the base frame x axis. So again OX represent the base frame x axis and OZ represent the z axis of the fixed frame. So everything is done with respect to the fixed frame. So the operation should be multiplied in the left side. So first is the rotation with respect to x axis is this one, and then translation along the x axis, that is a distance along the x axis, and therefore y and z are 0 0. Then a translation along z axis of the fixed frame. So again we multiply in the left side, O, that is 0 0 d is the amount of translation we are performing. Then a rotation about the z axis is given by this matrix. So we multiply all these 4. So after making these 4 types of motion, what will be the relation between the old frame and the new frame? That is given by the product of this 4 matrix, that is FTM. So we can adopt this same procedure for if you do the operations with respect to the current frame. Every time we obtain a new frame, and with respect to the axis of that frame, if you are doing the operations, we have to multiply in the right hand side, and successive multiplication will give the relation between fixed frame and the moving frame. So in either way we can obtain the relation between a given old frame and the current frame. So, with this we come to the conclusion about the relation between various frames of references, and which are represented in the form of a 4 by 4 matrix. So, this will be very useful in various robotics problems. So, in the next lecture we will see how this can be introduced in the robot kinematics and dynamics and various other concepts related to the robotics problem. Thank you.